Today, Mehrdad Ghadiri is going to give a talk on beyond submodular maximization via one-sided smoothness and Meta-Submodularity. Mehrdad is currently a second-year student at Georgia Tech, advised by Santosh Vimpala in the Algorithms Combinatorics Optimization program. And he finished his master's at University of British Columbia, I believe with Bruce Shepard, and did his bachelor's at Sharif. Interests are broadly in optimization, both continuous and discrete. So with that, go ahead and take it away.
Okay. Yeah, thank you, Matthew, for the introduction. This talk is about generalizing the techniques and methods in submodular maximization to other functions that are not submodular. Kind of the focus is on supermodular functions, but in general, the functions that we introduce are not submodular or supermodular or anything like that. This is a joint work with Richard Santiago and Bruce Shepard. The talk focuses on these two papers, but the main focus is the first paper. I mentioned some definitions from the second paper as well, because the second paper is the discrete version of the first paper, and maybe the discrete definitions are easier to understand. So we start from submodular functions. Basically, submodular functions are set functions that have this diminishing return property. It means that the marginal gain of adding an element is decreasing. One example to understand these functions better is coverage functions. As you can see in this picture, let's say we define a function on these three shapes, and the value of the function is the area that is covered by the union of those shapes. And as you can see, the area, the marginal gain of adding element C to just element A is the green area and the blue area, but the marginal gain of adding C to A and B is just the green area. So these coverage functions are submodular. Submodular functions in general have a lot of applications in machine learning, economics, combinatorial optimization, and many other areas. One important problem in combinatorial optimization, which has many applications, as I said, is constraint submodular maximization. So during the talk, we assumed that our functions in general, submodular or otherwise, are monotone and non-negative. And so the constraint submodular maximization problem is defined as maximizing a submodular function subject to some family of sets. And this family, maybe the most well-studied case is when we are talking about the independent sets of a matroid. So I'm giving a definition for matroids. Matroids are this class of family of sets that have these three properties. First of all, they're non-empty. Second of all, they have this hereditary property. So if some set is in the independent sets of the matroid, then any subset of that set is also in the matroid. The other property is the exchange property, the third property, which says that if two sets are in the independent sets of the matroid and one of them is bigger than the other, then I can add one element from the bigger set to the smaller set, and there exists such an element that S plus I is in the independent sets of the matroid. In general, if you don't know about matroids, maybe the easier way to think about them is that the family of forests of some graph G. And two more definitions is, one of them is the rank of the matroid. In this case, of the family of forests of a graph, the rank of the matroid would be the number of edges of a spanning forest. and the size of the smallest circuit, which we show by C, would be the size of the smallest cycle of the graph. Any questions so far? Okay. So as I mentioned, monotone submodular maximization is like an old problem which has many applications. So this old problem, so the first, maybe like the first actual result about them is from Fisher et al. In 1976. They gave like a half approximation for maximizing general monotone submodular functions subject to general matroids using a local search algorithm. And they gave a tight 1 - 1/E approximation for uniform matroids. So uniform matroids are just the family of sets with size less than or equal to K. The second algorithm is using Ghadiri. It took a long time, about like 35 years, to improve that half approximation for general matroids to 1 - 1/E. So to get like the tight approximation. And that framework uses the concavity and convexity of the multilinear extension of submodular functions in specific directions. I'm going to talk about that later, in more details. But for now, multilinear extension of a set function is defined to be like the expected value of randomly picking a set S from like a vector X. It means that if I have like a vector between 0 and 1 in the 0, 1 cube, I pick each element with probability xi, the corresponding coordinate, and then I take the expectation over f of s. So going beyond submodular functions, supermodular functions are like kind of the opposite of submodular functions. As you can see, the inequality we use to define submodular functions is exactly opposite for supermodular functions. The marginal gain for supermodular functions is increasing. Again, they have a lot of applications similar to submodular functions in machine learning, economics, a lot of other areas. But one problem with them is that they're not approximable within like even like, I'm not even talking about constant factor approximation, even like polynomial factor like n squared or something like that. In general, supermodular functions don't admit this kind of like approximations. Even like supermodular functions that have like nice structures are hard to approximate. One example of this supermodular functions with nice structure that seem to be hard to approximate is densest K subgraph. So suppose we have the adjacency matrix of a graph, and their goal is to find a subgraph of size K that has the most number of edges. This is the densest K subgraph. And the best known result is like an O of n to the 4th approximation. However, if A is metric, like let's say I have a complete weighted graph and the weights are metric, like let's say there are distances and that distance function between the vertices is metric, then there is a 2 approximation. In general, even if A is like sigma semi-metric, then there is a 2 sigma approximation for uniform matroids and then a 2 sigma squared approximation for general matroids. So sigma semi-metric is like a relaxation of the metric property. As you can see, like the inequality is the same, except there is like a sigma factor on the right-hand side for sigma semi-metrics. So it seems that what actually makes these functions approximable is the triangle inequality, or in general, the sigma semi-metric inequality. And it is not like the pairwise structure or any kind of like nice structure. So for like hints on how what can be done for these functions, we look at the framework for that 1 minus 1 over e approximation for monotone submodular functions. That framework has two phases. The first phase is a continuous optimization part, which works with the multilinear extension of the function. And basically, we're going to talk about like the actual algorithm a bit more later. But basically, it just uses the fact that the multilinear extension of submodular functions is concave in the forward direction, or like in like using mathematical language, it's like the inequality you see on the screen. Basically, if u is non-negative and x is like in the 0, 1 cube, then u transpose the Hessian times u is non-positive. So the first part, the continuous optimization part, uses this concavity in the forward direction. And the second part is to round the continuous solution to find an integral solution. And this part, which is lossless, we don't lose anything in doing this, uses the fact that the multilinear extension of submodular functions is convex in the EI minus EJ direction. For any ij, for any pair ij. So now the question is that can we use this framework for supermodular maximization or like non-submodular maximization? At first look, it might look that no, because we have this specific convexity and concavity in specific directions. So it might seem that we cannot use this for general functions. But we define some properties that actually allow us to use this framework for maximizing, like, generally a function, and the approximation factor we get is depends on some parameter. So here is the part that I'm going to talk about, like the discrete definition or meta-submodular definition, and also at the same time about the continuous definition. This is probably like the most important slide of the talk. And like, yeah, it is like everything is based on these definitions. So in the continuous side, we assume our function is continuously twice differentiable. And in the discrete side, we have a couple of definitions to like give our definition. First, remember that we only consider non-negative monotone functions. And the first like definition for that we need for the discrete side is B sub I of S, which is basically the marginal gain of adding I to the set S. And then we have the second order difference A sub ij of S, which is Bi of S plus j minus Bi of S minus j. This is exactly like defining marginal gain for the marginal gain. This is like the second derivative of, like the second discrete derivative of the function. And you might note that we can define submodular functions as functions where aij of s is less than or equal to 0 for any ij and s. So yeah, using these definitions, we can give our discrete and continuous definitions. So I'm giving these definitions at the same time, so one can see like the similarity between these. So on the left-hand side for the continuous functions, we say that the function is one-sided sigma smooth if for any non-zero x and any u greater than or equal to 0, we have this property that the second order directional derivative is bounded by some factor of the first order directional derivative. And on the right-hand side, on the discrete side, we have this second order difference is bounded by some regularized version of the sum of marginal gains for I and j. So basically, if x was the characteristic vector of S, then like the L1 norm of X on the left-hand side would be the size of S on the right-hand side. And then those U factors would just cancel if U was like some integral vector. And yeah, as you can see, these definitions are very similar. And I'm gonna like explain what actually does that mean for the discrete side, and like mention what is the like logic behind defining these things from the continuous side. So on the discrete side, we have this Aij of S here. So suppose this function I'm defining here is that complete weighted graph, and for set S, the value of the function is the sum of the edges in some clique with vertices in S. So there, if I write this inequality, basically it would be Aij of S would be the green edge, Bi of S would be the sum of the weights of the red edges, and Bj of S would be the sum of the weights of the yellow edges. And then we are doing this average. So basically, it is the average of Bi of S plus Bj of S. So if this was like metric or semi-metric, then I would know that for any vertex in S, the sum of the green edge would be smaller than the sum of the red edge plus the yellow edge. So basically, this inequality, this meta-submodular inequality, is an average form of sigma semi-metric property, or the triangle inequality. But note that it doesn't actually need the pairwise structure because of the way that we defined it. We defined it based on marginal gains, so it doesn't need the pairwise structure. On the continuous side, one can see that this definition that the second order directional derivative is bounded by the first order directional derivative is kind of reminiscent of the self-concordant functions, which are used for as barrier functions in interior point method for convex optimization. So over there, the third order directional derivative is bounded by second order directional derivative. Here it is the second order is bounded by the first order. So there is this connection between these functions and like barrier methods as well. So yeah, having these definitions in mind, we go to see like what is the property, what is nice about these functions that make them approximable. So the key property of one-sided smooth functions that we use in the analysis of our algorithm is this. Basically, it says that the first order directional derivative at points close to x is bounded by some factor of the directional derivative at points at x itself. So one can see that this bound is exponential in sigma, but when like sigma is like constant, it is like a constant bound or something like that. So yeah, as I mentioned, we use this property to bound the Taylor expansion, which is like basically the main step of our analysis in at least the continuous part of our analysis. And I'm going to give the proof of this. just to see like how we use the one-sided smoothness to get this. So the proof is kind of not that hard. It goes this way. So we defined the gradient in direction u as like the function g of t, which would be u transpose the gradient of f at x plus tu for t like between 0 and 1. And then one can see that derivative of t would be u transpose the Hessian times u. And then for any number h greater than 0, we will have this chain of inequalities. So basically, as we said, g prime of t is like the second order directional derivative, which using the one-sided smoothness property is bounded by the first order directional derivative. And so that is like the first inequality. And then that is equal to sigma times L1 norm of u over L1 norm of x plus tu times g of t, because u transpose, like the definition of g of t, just gives us that equality. And then, as I said, because we assume the function is monotone, g of t is like non-negative. So we have that last inequality for any positive h. And then just moving g of t plus h to the left-hand side, we get this inequality, which says that g prime of t over g of t plus h is less than or equal to sigma times that fraction of L1 norms. And then we just integrate both sides. I'm not gonna like go over the integration. It is just a straightforward like integrating both sides, and then one can see, okay, because like both hand sides are like because we have this over like the whole domain of the integral, the inequality holds for the integral itself. So we have this, and then we take like e to the each side because the exponential function is monotone, we get this. And then because g of epsilon is u transpose gradient of f at x plus epsilon u, and g of 0 is u transpose the gradient of f at x, we get this for any h greater than 0. And then we just take the limit of h at 0, and it gives us this inequality. And this is like the key property that we use for the continuous part of our algorithm. So now we jump to like the continuous part. So this is basically the algorithm that has been used for the 1 minus 1 over e approximation for monotone submodular functions. There's only like a small tweak in the algorithm that I'm going to explain and see how can we use the that key property of one-sided smoothness to like show that this algorithm also works for one-sided smooth functions. So basically, the algorithm starts from some non-zero point, and we pick the non-zero point as some constant fraction of the longest vector in our polytope. So let's say I have like a downwards closed polytope, and I'm trying to solve the problem for a downwards closed polytope. And I pick the longest vector in terms of like the L1 norm in that polytope, and I multiply that vector by some constant between 0 and 1. And I start from that vector. In a standard continuous greedy, they just start from point 0, like the origin of the space. And then we take a path that maximizes the directional derivative. So it is the vector in P that maximizes V transpose the gradient of f at x. So this step is exactly the same as the continuous greedy. Because of because in the first step we start from a non-zero point, we call this algorithm jump start continuous greedy. And yeah, basically we take this path and yeah, basically one can note that this is like a Frank-Wolf algorithm as well, because we take the path that maximizes the directional derivative. And this gives us this bound on f of x1, which is the output of our algorithm. So f of x1 is greater than or equal to that 1 minus the exponential of that term times the optimum value of the function. And if we put alpha equals to a half, it gives us this second bound, which is like O of like 3 to the sigma. So this gives us like an O of 3 to the sigma approximation. One important thing is that, as you can see, the approximation only depends on this parameter sigma. It doesn't depend on the size of the problem like n or anything else. It just depends on this sigma. And like, as we mentioned, like the sigma for metric functions is like 1. For sigma semi-metric, it is like sigma. So it is, in many applications, it is like a constant. But it is still exponential in sigma. So one might wonder like if we can improve this like with more properties. So one property is that we can add to improve the approximation factor is the non-positivity of the third order partial derivatives. So note that for submodular functions, we have the non-positivity of the second order partial derivatives. And it is just like we are going one order ahead, and we talk about like the third order partial derivative instead of like second order. Also, this is equivalent to the definition of second order submodularity, which is defined by Korolla, Mirokni, and Zadi Mogaddam. And adding this property to the previous property of like one-sided smoothness, we can show that our jump start continuous greedy finds an approximation which is like linear in sigma. And actually this is like tight up to constant factors. So I'm gonna like talk about the main step of the proof of this algorithm, which is kind of like the main step of the proof in the 1 minus 1 over E approximation. So suppose f of x star is equal to the optimum. I mean, like x star is the optimum. X is some point in the polytope, and U is like x star minus x. And we take the positive part of that. That like V is like the entry-wise maximum for a vector. So if like for some coordinate x star is less than x, we just take 0 for that coordinate. And basically, for submodular functions, we have this chain of inequalities. So basically, because the function is monotone, f of x star which is equal to opt, is less than or equal to f of x star or x, or f of x star and the maximum of x star and x. And then we can write the Taylor expansion of this function. And this is just a second order Taylor expansion. It holds for some epsilon between 0 and 1. And then, as we mentioned, because the second order directional derivative is non-positive for submodular functions, we have the last inequality. So this gives us this bound that going in the direction of U transpose U transpose the gradient of f at x increases the value of the function proportional to opt minus f of x. So basically, going in the direction that maximizes this would be better. It would increase the value of the function at least proportional to opt minus f of x. So this is the main step of the proof for continuous greedy for monotone submodular functions. So we generalize this to one-sided smooth functions. Basically, for one-sided smooth functions, we write the Taylor expansion for like the first order Taylor expansion, and we use the key property that we proved like a few slides ago. And yeah, basically, opt is less than or equal to f of x star or x, and then we write the first order Taylor expansion, which holds for some epsilon between 0 and 1, and then we use the key property to bound that directional derivative at some point close to x by the directional derivative at x. And then we can see that we actually can bound that factor for directional derivative, that L1 norm fraction. Why can we do that? Because we start from a non-zero point. So basically, because epsilon is between 0 and 1 and u is non-negative, we have the first inequality. Then the second inequality is actually equality. We just can separate the L1 norm in the numerator. And then we have the third inequality because x, for any point in our path, we don't decrease any coordinate. So any of those points are, the length of them is less than x0. And then we know that x0 is at least 1 over alpha of any vector in our polytope, because we think about how we picked x0. We picked the longest vector in the polytope and we multiplied that by some constant alpha. So basically this says that any point, this L1 norm fraction is less than or equal to alpha plus 1 over alpha, and alpha is the constant we use to find the first point in our path. And then combining these two inequalities says that going in the direction that maximizes the directional derivative at least increases the value of the function by some fraction of opt minus f of x. And as you can see, if we pick like alpha equal to a half, then that is like 1 over 3 to the sigma, that that factor. So this is like the main step in the proof. I'm not going to talk about like the other steps of the proof. Instead of that, I want to go ahead and see application of these functions. So one applications of these functions is for the functions which we call discrete quadratics. So these are the multilinear extension of like the diversity functions I talked about, which are like we have a weighted complete graph, and let's say I have some weights on the vertices as well, and then I pick some vertices and just take this over all the weights of the edges and the weights of the vertices. And that is like a discrete function. And here, if I take the multilinear extension of that function, it is these functions, which we call discrete quadratics. So here we assume that A, this matrix of weights is sigma semi-matrix, and A of A and B are non-negative, and one can see this satisfy the conditions of the second theorem, the theorem that gives us a linear bound, like a linear approximation in terms of sigma. So why? The reason is that the sigma semi-metric property gives us the one-sided smoothness, and one can see the third order partial derivatives for these functions is just 0. So it is non-positive. Also, one can see that this definition, this is basically equivalent to second order modular functions defined by Korolam, Mirokni, and Zadi Muqaddam. And so basically, because this satisfies the conditions of the second theorem, we can find a linear approximation in terms of sigma for this continuous function. So we ask, can we round them as well? Like, we're interested in finding an integral solution, right? So the question is if we can round them. The answer is yes, and but like how we can round them is a bit complicated. So usually in many rounding methods in submodular optimization, we just round the function. It is lossless, and we basically get the approximation factor that we got for the continuous phase. But here, this is not the case. Actually, there is no lossless rounding for these functions. And the rounding method that we give is actually the best of two rounding methods. So we give two different rounding methods. Each gets a different gap, and then we take the best of them. Like, we run both rounding methods, and then we take the solution that is better. As you can remember, R is rank of the matroid, and C is the size of the smallest circuit of the matroid. In terms of graphic matroids, which are the family of forests of the matroid, forests of a graph, R is the number of edges of a spanning forest, and C is the size of the smallest cycle of the graph. And basically, one of our rounding methods gives us a gap of R over C minus 2, and the other one gives us a gap of 1 plus sigma over R. And one can see that R is either less than or equal to a square root of sigma or greater than or square root of sigma. If it is less than a square root of sigma, then R over C minus 2 is less than a square root of sigma. If R is greater than a square root of sigma, then sigma over R is less than a square root of sigma. So the total bound is, for the rounding part, is O of a square root of sigma. However, this is like a pessimistic bound, because, like, for example, for uniform matroids, C is equal to R plus 1. So the first bound of R over C minus 2 actually gives us like a constant gap. So combining this with the continuous part, this gives us an O of sigma to the 3/2 approximation for maximizing this so-called sigma semi-metric diversity functions, or discrete quadratics, which is an improvement over like the previously best known approximation of sigma squared. And I'm going to talk about the rounding methods that we use, which are based on are inspired by two different rounding methods that are used for like rounding linear objectives or submodular objectives before. So the first one is swap rounding, which gives us the bound of 1 plus sigma over r. So in swap rounding, it works like this. By Ghadiri theorem, let's say we have this vector x, which is like our solution, our continuous solution. By Ghadiri theorem, we have this equality that we can write this vector as a convex combination of at most n plus 1 bases of the matroid. And this is because like our space is n-dimensional. So swap rounding works like this. It starts from two of these bases. It merges them to one base. So let's say we have three bases in this convex combination, I1, I2, and I3. And a convex combination of them is X. We merge I1 and I2 to get I2 prime. And then we get a new vector X prime, which is a convex combination of I2 prime and I3. So the weight of I1 and I2 were lambda 1 and lambda 2. The weight of I2 prime would be lambda 1 plus lambda 2. So how's the merge goes? The merge goes like this. So we have these two bases of the matroid. So each of these ellipses I'm showing here is, let's say, is one of the bases of the matroid. And so they have like some intersection and some parts in like their symmetric difference. I know because this is a matroid, by a strong exchange property, there is two elements in these bases that I can kind of swap or something like that. It is not kind of swap. It means that I can remove, like, let's say, the green element from I1 and add the red element, and it is still a base of the matroid. And I can remove the red element from I2 and then add the green element to it, and it is still a base of the matroid. So the swap goes like this. I do one of these like things I just mentioned. I either remove the green element from I1 and add the red element to it, or I remove the red element from I2 and add the green element. So this step increases the size of the intersection of these two bases. So after some step, at most R steps, I will end up with just one base, which has a weight of lambda 1 plus lambda 2. And we show that we can do this and until we get just one base with the weight of lambda 1 plus lambda 2. And we show that the loss of doing this for one step, let's say in the first step, I do this for I and j. Like element I in I1 minus I2 and element j in I2 minus I1. The loss of this step is lambda 1 times lambda 2 times a of I and j. And the total loss is like is lambda 1 times lambda 2 times the size of this matching. Like I have this matching where I take the pair of elements and I do this step of like removing one of them and adding it, adding the other one to the set, to the bases. And so the total loss of one merge, or like the first merge, is lambda 1 times lambda 2 times size of that matching. The loss of the second merge, because the weight of the new base is lambda 1 plus lambda 2, is lambda 1 plus lambda 2 times lambda 3 times the size of this new, like the matching for this second merge. And so on and so forth. The loss of the nth merge is the sum of lambda 1 to lambda n times lambda n plus 1 times the weight of the matching for the last merge. Summing over all of these, the total loss is like lambda I, the sum of lambda I lambda j, lambda I times lambda j, times, like, let's say, the maximum between all of these matchings. So let's say M star was the matching that had maximum weight among M1 to Mn. Then we can show, because this is a convex combination, the sum of lambda 1 to lambda n is equal to 1, that the total loss is less than a half times the sum of the weights for this maximum matching. And then the algorithm is this. Suppose B is the final base obtained by the merging process after we merged like all of the bases. And let's say I and I prime were the bases corresponding to the matching M star, that maximum matching. Then I take this new base. It might seem weird that I just don't care about like the vector anymore, and I define this point half of I plus half of I prime, and then I merge them and I get this other base B prime. And then I return the best of B and B prime. So why does this work? The reason that this works is that that matching, the sum of the weights of that matching is bounded by some factor of f of B prime, where B prime is the result of merging half of I and half of I prime. And then the whole thing gives us an O of 1 plus sigma over R, a rounding gap. So this is the first rounding method. The second one is based on approximate integer decomposition. I'm not going to go into much details for this one. Basically, what we do is that we find a set of bases of the matroid and some numbers. This is not necessarily a convex combination, but it is some numbers mu I, where the sum of them is less than or equal to some number k, and the sum of mu I times f of base I sub I covers the linear and quadratic part for the discrete quadratic function. So what does this mean that it covers this? It means that for each pair ij, we cover A of I and j as much as, at least as much as xi, xj. And we cover bi at least as much as xi. If we can do this, then one can show that this gives us a rounding gap of k. So we show that this k for our problem is r over c minus 2. So this second approach gives us a rounding gap of r over c minus 2. So we have matching lower bounds as well. Basically, for both phases of the framework or algorithm, which is the continuous optimization part and the rounding part, we show that there are like lower bounds, and they are like tight, like the bounds that we gave, like the upper bounds we gave, are tight up to constant factors. And basically, you cannot do better than O of sigma for the continuous part, and you can't do better than O of square root of sigma for the rounding part. This gives us this conjecture that probably our approximation factor is also tight up to constant factors. Not that like the tightness of each phase doesn't imply that the whole thing is tight, but we have this conjecture that sigma to the 3 halves is actually tight. Another lower bound is that the discrete quadratics cannot be maximized within a factor better than 2 sigma for uniform matroids. So basically, there is still this gap between the upper bound and the lower bound, because the best lower bound that we have is this theorem, which is for uniform matroids, not for general matroids. So this best lower bound is like we can't do better than 2 sigma, and the best upper bound is sigma to the 3/2. So there are some directions for like future research that I'm going to mention as like the last slide of the talk. It is that so one thing that might be interesting is that giving a rounding for general one-sided smooth functions, and because the only rounding that we gave was for discrete quadratics, and in general for like more general polytopes, like let's say intersection of matroids, or like P systems, or like these general polytopes. Another one is to improve the approximation factor for general one-sided smooth functions. So as you may remember, for general one-sided smooth functions, our approximation factor is exponential in sigma, but it might be possible to improve that, or improve the 3 to the sigma, like get, I don't know, 2 to the sigma or something like that, improving the exponential factor, or improving it to some polynomial factor. The third direction is closing the gap for discrete quadratics. As I mentioned, the lower bound right now is sigma, and the upper bound is sigma to the 3/2. And maybe the last direction is to finding more applications for these functions in, I don't know, machine learning, economics, game theory, or like other areas. And thank you for listening. Any questions?
Cool. Okay, let's first give a round of applause. So yeah,
Sounds good.
thanks for that. That was a nice talk.
Thank you, Mehrdad.
Thank you.
Yeah, any questions from the audience? Okay, well, I had one at least. But yeah, so I mean, this rounding like via like constructing a new independent set from a like strong exchange property, has this been used elsewhere? I mean, it's a very cool, clean idea, at least to get from.
Yeah, actually, swap
basis to a new
rounding,
one.
I think the first time they used it was for linear objectives, and then they used it for submodular objectives like later. And point is that like for submodular objectives, because of that convexity in the EI minus EJ direction, we have that lossless rounding. All of this like pairwise kind of roundings gets like a lossless rounding. But here we don't have that, and we get like this force bound. Yeah.
Cool, thanks. Any other questions? Okay, well, with that, I guess we can end the recording. And yeah, thanks again for the nice talk.
Okay, thank you.